Let's move on to the next talk, and that's by Amy McAdam, and she's going to give us an overview of the Lunar Water ISRU measurement study, LWIMS, LWIMS. Okay, Amy, please take it on.
All right. Hi, everyone. Can you hear me okay?
Yes.
Yes, great. Thank you. Today I'm going to give actually a shorter version of the executive summary of a then even larger product that's coming out very soon to the community from the LWIMS group. And so I'm just here representing this great group of people you see there at the bottom of the slide and presenting these slides about, as you said, LWIMS, Lunar Water ISRU Measurement Study, and the topic is about establishing a measurement plan for the identification and characterization of water reserve on the moon. Next slide. So I'll go over especially these beginning slides really quickly, and I'll try to leave some time for questions at the end. There's a lot to cover here, and so if there are additional questions, like they're just saying after, if we run out of time a little bit, definitely feel free to follow up in other ways, and we will make sure to answer them. But so really briefly here, so water has been identified in the permanently shadowed regions, PSRs, and adjacent areas, and this can be significantly enabling for lunar sustainability. But the development of ISRU architecture, so mining, CONOPS, harbor design, requires knowledge of several aspects of the water that we don't yet, have a full enough understanding of, such as water distribution and heterogeneity, form, the characteristics of the potential mining locations, etc. You can see all the details there. And so the problem statements for the study. We have this single surface data point from the L-cross impact. But there is a significant uncertainty in the type amount, physical parameters, and distribution, lateral and vertical, of the water and volatiles in PSRs. And more ground truth is needed for this information before ISRU hardware and CONOPS can be designed. And while current and future lunar science instruments and missions can definitely provide critical information, those science-focused efforts may not be sufficient for ISRU goals. So overall, water has been identified as a resource, but its potential for ISRU requires identifying and finding and locating a reserve. So next slide. So this is just a very, very brief overview of the current knowledge state of lunar polar water. So there are the four types there. So surface frost, shallow bulk water, deep bulk water, and pyroclastic deposits. For this study, we focused on shallow bulk water, which we defined as water in the top meter. And we focused on this because it trades best for ISRU. We have four data sets related to shallow bulk water, and they're summarized in the table there that I won't go over in detail for brevity, but I'll go over some of these bullets on the side there briefly. Of course, we have all this great data from neutron spectroscopy and derived water equivalent hydrogen, but we can't derive from this sufficient accuracy and depth distribution that is needed for ISRU needs, and also the footprint is sort of regional, and we expect important local heterogeneity to impact ISRU needs. We have radar data, which may suggest large runs of water, but surface roughness in many cases can also produce a similar signal. And so in summary, the resolutions from current data sets are insufficient for ISRU reserve definition. So next slide. And so this is just to point out there's these great commonalities and also differences between the measurements that are needed for science and ISRU. Measurements for science tend to be towards objectives that are sort of broader, where we need a wider variety of data to understand natural processes, and there's some examples there. Whereas ISRU objectives tend to be more targeted and focused, and there's this essential relationship to engineering that you can see borne out in those examples. And so, there are definitely some critical commonalities you can see in the middle there, but important differences to keep in mind. Okay, next slide. So this outlines our measurement plan structure, recommended measurement plan structure. And so in the middle of this is importantly, and this comes up many times, is this predictive model. So this is this water favorability map. It's similar to a mineral favorability map in terrestrial exploration. And intrinsic to this plan are the continuation of orbital measurements, new measurements, and also expanded work on existing data sets. But another key part of this plan, of course, is that you can see there these different types of landed missions that we recommend here. So type 1 missions are landed reconnaissance missions, and the goal of these is to validate your predictive model. Then type 2 missions are focused exploratory. So the goal of these missions is for these to go to a site that you identify based on your validated model from interaction between type 1 and the model, and then verify the model water prediction at that site. And then type 3 is your detailed reserve mapping mission or undertaking. And so here you would do a detailed mapping of the ISRU reserve. Mobility would be required for this type of mission. And this would also be where you, for example, do detailed measurements of like geotechnical parameters and things that you'll need to do ISRU, and the end goal there in the dark orange bubble, putting your ISRU power plant in a location where, the goal is to have a mapped reserve. And the goal for that is 2028, as you can see there. Okay, next slide. And so this was discussed in the plan that I just showed, but in a great flow chart that shows risks and different paths. And I won't go over this in detail, again, to save a little bit of time, but you can see shaded in red there, the path that is equivalent to kind of what I just showed. So, as a minimum, we recommend 3 landed missions, 1 of each type in that path, as the sort of low, medium risk path. And of course, the specific path that ends up being followed will depend on direction from NASA management and considerations of allowable risk and timeline and cost. Okay, next slide. And so with that in mind, I'll discuss our findings and recommendations. And I'll summarize some of these points to save a little bit of time and try to leave some room for questions. So our first finding was that, current data sets are insufficient to define a reserve, and there's some details there that we were just discussing. So schedule is a key driver here. So 2028 is the target for this ISRU power plant. So this can limit options for instruments and ways to implementation options. And so this may lead to a preference for the reuse or reflight of instruments and hardware to minimize risk and improve data interpretation. The plan has to be reflective of the risk posture and the results returned, and importantly, the development of the ISRU production systems will need to occur in parallel with this reserve identification in order to meet this tight schedule, and delays to this measurement plan will result in higher hardware risk. Was there a question? Okay. Then the third finding there is that existing measurement techniques can achieve the data needed, but they need to be adapted for lunar application, for example, operation and PSRs. And water quantification techniques that involve sample heating will likely produce the highest accuracy, but these are least developed for these applications. And so there's work needed there. Next slide. Okay, so recommendations. To meet the aggressive schedule, a focused effort must be implemented that involves all mission directorates. So STMD for ISRU hardware development, HEO for implementation of ISRU, and SMD for volatile measurements, and overlap science objectives. And additional regional data sets, orbital data sets, are of very high value to reduce risk, and we recommend that missions, so Lunar Map, Lunar Flashlight, Lunar Ice Cube, and the Trailblazer concept should all go forward. We recommend supporting ISRU relevant technologies and PRISM and Luster and similar programs. And then overall a summary, so we recommend this best path, this low, moderate risk path, to proceed with the currently planned CubeSat and SmallSat missions to advance those regional data sets. Very importantly, support development of the predictive model capability as soon as possible, perform Viper as the first type 1 mission, and then perform this minimum of 3 land exploration missions, type 1, 2, and 3 that were discussed. Next slide.
1 minute left.
Recommendation. Yeah. Was that my time? Time warning?
Yeah, 1 minute left.
Oh, geez. Okay. Sorry. Okay. Recommendations for future work. So we recommend the formation of a standing working group, a multidisciplinary one, that will work on the definition of a reserve, and how there's some differences in how you might define this on Earth and Moon and Mars, and so there needs to be a consensus definition developed that's dependent on the risk tolerance of the exploration program, and it should involve all stakeholders. The development of a mineral model, or what we call predictive model, is essential and would need to be continuously updated in a timely way. And then finally, again, coordination is needed between all mission directorates to maximize investment, minimize overlap, and clear handoff and roles between them should be defined. And that is all I had. There may be a tiny bit of time for questions.
There is
Okay.
there's probably time for one question. There's one that came up in the chat. It's
Okay.
Are cleanliness standards being developed that address common water contaminants found in the polar volatiles, such as H2S, ammonia, mercury, etc.?
I know that there are ISRU folks that are considering those contaminants and how they may be, scrubbed from water to purify it, or even maybe used as a different kind of resource. Yes.
Okay, so they're being addressed, is what you're saying.
Yes. Yeah. There are several projects that I know of that are working on that. Mm-hmm.
Okay.
It's a very important point.
Okay. Thank you very much.